Hi everyone. So um we're gonna start our class. This is our seventh session together, and today we're gonna continue discussing about the two variables bivariate data, and now we're going to make some predictions. And I mean we discussed correlation coefficient before, but when do we use that information? I mean, it's good to know that there is a relationship, but that's not our ultimate goal, right? If we were looking at a relationship, we want to be able to use that data or use that analysis to predict or to make a guess about future or any kind of data that we have based on the data we have, right? So that's what we're gonna do today. So um, let's just start with the homework to refresh our memory just a little bit. So let's just look at this. All right, so this was the first question, and the following table shows the number of cell phone subscribers, number of persons in jail, and number of what is it? More registered motorcycle, right? So these are the numbers that we have, and we also have the year, right? And first you were to create, oh, I spelled that wrong. Create a scatter plot and identify the kind of association using correlation coefficient, right? And there could be more than one relationship. And I gave you a little hint that inmate, the number of people in jail is the y-axis, on the y-axis, meaning this is the output, right? So we can use either this or the year as the variable, and this is how it looks like. And if you look at the graph, it looks pretty straight to me, right? There seems to be a pretty strong relationship, linear relationship, right? And if you were to draw a trend line, right, it's more visible here now that there is a line. And from here to, if you do a trend line, we see a positive correlation. And if you look at the sorry, let's look at the R. I don't know why I don't have this, but we can easily look it up, right? So if we are looking for the R value, right? So let's just do this one, correlation, and then we give it a range. This down to here, enter, and we see that there is a strong positive relationship. So if it's close to 1, um, I'm not sure if I discussed this before, but yeah, we can talk about this. Let me just write this down first. And for correlation here too, right? So range is this and motorcycle. Okay, and here it's pretty high too, right? So this was cell phone versus inmate, and this is motorcycle versus inmate. So if you go back to our note, can write that down. Um, okay, so when we're talking about correlation coefficient, right? This is notated by R. R is always greater than or equal to -1 or less than or equal to 1. Alright? And when we're looking at just a relationship, right? When R is negative, that means what? There is a negative relationship. And when R is positive, there is a positive. And just looking at the absolute value of R, so without the sign, if it's close to 1, then this is a strong linear relationship. And if it's close to, if absolute value of R is close to 0, there is a weak or no linear relationship. And we saw the graph from last class, so I'm not going to repeat myself, but that's pretty much it. Even even if it's negative value, it doesn't really mean that there is no relationship. There is a strong relationship if it's -1, but it's just that there is an opposite. So it looks like this. This would be R equals -1. And here, this would be R equals +1. Right? So that was correlation coefficient. Alright, so today we're going to talk about oh yeah, before we do that, we forgot to go over question 2 and 3. So let's quickly go over it. Right, so this table shows the amount of municipal slide waste created. Right, so this is the year, the garbage, and population. These are all in millions. Right, so I did garbage versus year and garbage versus population, and we see that there is a very, very strong relationship from the data, right? From the scatter plot. So if you draw the trend line, you see that this is pretty close, right? And same for this. I'm sorry, this is pretty big. Yeah, so these are pretty close enough. And if you look at the R value, I just used the correlation function. This is garbage versus year is 0.996, and that's very, very, very close to 1. So this is almost perfectly linear. And same thing with the other one, garbage versus population, it's 0.99. Right? And there is a positive correlation because R value is positive and its graph is going up. And also looking at lurking variables. So when we're looking at garbage versus year, what we are forgetting about is the population. So this, when we're just looking at these two variables, this could be the lurking variable because we see that from here, population does have an effect, right? And same thing. So when talking about garbage and population, the time also can be the lurking variable. And in fact, time and population, these two are related. So we call that multicollinearity, but I don't think we are going to talk about that here. But there is a relationship between the year and population. So when we are analyzing this data, we have to factor that into account. And although we're not talking about the numerical measurement of the relationship between year and population, when we are making a conclusion, we have to mention that there seems to be a relationship between year and population. Right, so that was that. And question 3 was, yeah, this is the gold, silver, bronze medal. First of all, just looking at the score, I made it that as the following. So E3 times 3 because we're multiplying that by 3, and F3 times 2 because we're multiplying that by 2, and just G3. And if you copy this all down, you get the total score. Alright? And here, I just filtered it out, and I copy the data when I filter for swimming, and this is the value that I got, age and total score. And here, this is this is data I got from archery. Alright, so again, R is pretty straightforward, just do correlation. And if you did it manually, it's always the same. just check for the answer if it's correct, if it corresponds to this value, and we can comment on this because this is a very, very small number. This is almost close to zero. And if we're looking at the scatter plot, there is something going on here. You see there is high density from 15 to 30, and you see there's stuff going on around here, but there is no linear relationship. So if you were to um, draw the trend line, it's here. It's like there is not much going on in terms of linear relationship. And same thing here. This is very interesting because um, it's all scattered apart, but there seems to be no linear relationship, and this is um, r equals negative. This is negative instead of positive compared to the other one. Um, so if you were to draw the trend line again, there is something like that, but that doesn't really represent the data very well. So that was the homework, right? So today we're going to talk about something new. And we call that linear regression. So what we are doing essentially when we are doing linear regression is we're trying to make a prediction. Prediction for an un for an unknown value. Alright? So this is only applicable when we have a strong linear relationship. Only if we have a strong linear relationship. And we can figure this out by doing what? By looking at absolute value of r. If absolute value if absolute value of r is close to 1, that means that there is a strong relationship, right? And we want to use that because what linear regression is doing, you know what? Okay, so why don't we just copy and paste a scatter plot from one of these. So why don't we choose yeah, let's choose this one. Garbage versus population. Okay, so I'm gonna screen clip this scatter plot. And then let's go back to our notes. Okay, so it's right here. Right, so let's let's look at this scatter plot. And now we're talking about the linear regression. Linear regression, what it's doing is it's making this line here. And we see the line right here, and it was given by the Excel function. And we make this line, and we call this best fitted line, okay? And how do we find this? This is the question, right? How do we figure out which one's which? Like we want to know if it's which one has the best fit into the set of data. So what we use is the following, right? And before I give you the formula, I just want you to understand the concept. So this is it's a little difficult because these are very, very well fitted, but you see the line here, the dotted line, and you see the observation, and observations are noted by the dots. And what we look for is we look at these distances, right? We look at the distance from here to here and here to here. And I'm going to draw I guess a zoomed in version of this. So if it's the line is like if the line is like that, the observations are somewhere here. We have one here, 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 something like this, right? And obviously this is not drawn to scale, but if you look at this, we have distances here, right? And we call these distances errors. Why? Because this is a model that we're using. The straight line is the model that we're using, and these are the real values, correct? So the difference between these two are called the errors because that's how much we didn't cover, right? But this here the error is negative, and here the errors are positive. So if you add these up, right? Negative values, they're going to cancel out the positive values, so you're going to end up having a very small number, and we don't want that to happen. We want to see how much these observations are from the fitted the model, which is the fitted line. So what do we do is we again square these values. And the reason why we're squaring these values first is to get rid of the signs. So it makes it all positive, and that's what we want because we want to add the numbers and we want to see the absolute value of these errors, not with the sign. And because with the sign, it cancels out. And second, we want to kind of how to maximize. No, not. Let's not use the word maximize. We want to penalize for bigger values, right? So let's just think about it. If the distance between, I don't know, this observation and this point right here on the graph is, say, it's, I don't know, it's 1. Whereas from here to here, see, the value here is 3. So if you square these numbers, if you square 1, you're just gonna get 1. But if you square 3, you're gonna get what? 9. And that's exactly why we're using squares, because we want to penalize for bigger errors, or rather not values, but bigger errors. Okay, so we square those numbers. And what the model does, or the Excel does, is it tries to find the line where it minimizes the error squared. Okay, the sum of the error squared, and we call that sum. We so here, let me just go down, choose this, and then okay, so linear regression tries to minimize the sum of all squared errors. Okay, and that's exactly how we come up with this line. So that's the basic idea behind it, and we are going to do an example where we're going to find the the line, the function of the line, right? So, okay. So just looking at this line, if it's a straight line, for a straight function, linear function, what do we use? We have y-intercept and the slope, right? So we're going to have the same. So we call this y hat. Okay? Any values, so y hat is any values on the line or the model. We might call this model because we're the one who came up with this to explain these data, right? Y hat is always predictive value, right? So aka also known as predictive value. Okay? And y hat equals, we're going to have beta 0 and beta with the hat because these are all assumptions or the predictions that we're making. Beta 0 is exactly y-intercept plus beta 1 hat times x. And x, in this case, represents the population, right? So this is a formula, and how do we get these numbers? Let's look at this. Okay, so this is the formula. So equation of the line fitted by least squares. So let me just write that down again. B sub 0 hat plus beta sub 1 hat times x, and the slope is beta 1 hat, and we find this by standard deviation of xy and standard deviation of xx. And this is, we learned this before. We find this value by subtracting x bar from xi observation, ith observation, and we multiply that by y. And we did this before when we were doing the looking for the correlation. And here it's xx, so it's x minus x bar squared. Okay, and intercept is always easy because we are just looking for a value that would make the line go with the value. So this is 0 ahead, b0 ahead. So this is exactly it. Okay, and let's just look at an example to illustrate this. So why don't we just go to Excel? I think I have the file here. Is this the right one? Concentration time. Okay, I think I have it here. Alright, so this is the value we have. Okay, so let me just drag this down. And let's do an example with this. Okay, so example. Alright, so we have the concentration of X and drying time. This is for paint, so just giving you a background information. So how much of the solvent, how much of the chemical that are dissolved in the paint, and that's noted by 0, 1, 2, 3, 4, and drying time, and how long it takes to dry. So that's in minute 1, 5, 3, 9, 7. So this is the data that we have. And what we are looking for is the linear regression. We're looking for the equation, right? So therefore, we're looking for the equation. But before we do anything, we have to make sure if the relationship between these two numbers are linear, right? So in that case, we have to look at the correlation coefficient. And so to do that, we go back to Excel. I'm going to make another tab for this. Okay, so I'm just going to label this paint, and let's work on this. So let's first of all, let's just find the computer is being very slow again. The correlation between the two. So we would do correlation, and then you choose the array, and the next array is this, and we see 0.8. And this is a pretty high number. This is pretty close to 1. So it is safe to use linear regression. Alright, so let's go ahead and work on. Let me just copy and paste this down here. Okay, so R equals that. Okay, so let's work on our linear regression by hand. Okay, let's move on. No, let's go back to our notes, and to do that, we're going to do it by hand before using Excel. So just bear with me. Okay, so here I'm gonna make more columns, because when we are looking at this, right, this formula here, what we need is we have to have x bar, y bar, and then we're summing them all, right? So you know what? Actually, why don't we just use Excel for this? I'm sorry, I keep changing my mind, but I think it's better to use Excel because we don't want to waste time calculating all the stuff. So let me just write down the equation right here so we don't get confused. So I'm going to do that right here. So slope is sigma x minus x bar and y minus y bar, and then divide this by sigma of x, change this to x minus x bar squared, right? And this is standard deviation of xy and standard deviation of xx. Okay, and you don't really have to know what these two represent, because we're going to learn about this in detail later on, but that's just how we that's just how formula works. So xy, so this is the standard deviation, how it varies between data x and y, and here it's how it varies within itself. Right? So what we're gonna do here, just looking at the formula, so first of all, we need x bar and y bar, right? So okay, so let's do that. This is x and this is y, so we're gonna do x bar and y bar. So it equals average of these 5 values, and the average is 2 in this case, and here average of these 5 values again is 5, right? So why don't I just make another column and say these are the averages. Okay, so average, okay, so we're gonna do x minus x bar, right? And we do that by selecting this minus x bar, and then lock this value, and we're gonna drag it down all the way. Here this is y minus y bar, right? And we do that same. This is the y. These are the y values. Minus y bar, and lock the value. Lock the y bar value because we don't want that to change. Drag this down. And this is very similar to what we did before for correlation coefficient, right? And then we're gonna do this. We're gonna multiply these two, right? So column D times E. So we just simply multiply with the star. Okay, so multiply these numbers, and we're gonna get the sum. So here is the sum of all. So we're gonna use the sum function and drag it down, and we get 16. So the top part here, sigma, so standard deviation of x, y is 16. And we have to get the same for as x, right? As, as should be as xx. But yeah, I don't want to bother doing that because it's going to cause me some trouble again. So do that, and to find x as xx, we multiply x minus x bar twice. Oops, I did that wrong. Should be here. So x minus x bar to the second power, and we do that again times d2. We do that for all, and we get the sum of, you can just drag it from here, 10. Okay, and to get beta 1, just write it down here. Beta 1 equals sum of all these values, so that's this one right here, divided by this number, and we get 1.6. So 1.6 is our, what is the slope of this function. And next we have to do the intercept, right? So let's go ahead and do that. Intercept is just making this function equal to 0. So pen, let's go back to pen. You just write that down again, xx, and 0 equals y bar minus b1 hat x bar. Okay, so if you do that, let me just write that down. So we found out that y bar is what, 5, and x bar is 2. So 5 minus this b1 beta 1 hat is right here, 1.6. 6 times, what is it? X bar is 2. 2, and what do we get for b0? The 0 hat? That's going to be 5 minus 3.2, so that's going to be what? 1.8. So that's our value. So if you write the whole equation down, y0 hat equals 1.8 plus 1.6 x. This is our linear regression. So it's pretty simple. But the good news here is that we are never going to use this, use the mathematical way, because Excel is great. Excel has everything already. So let's just look at how we would do this without going through all this. So if you just understand the concept, it doesn't really mean much to calculate all this because we have it already, right? So just go to data analysis tab, right? This 2-pack, if you haven't installed it yet, I want you to go again. Let me show you again. So go to file, go to options, right? And go to add-in, and we are going to choose, so manage Excel add-ins, and we're going to choose analysis tool pack. Okay, just press OK, and if you go to your data tab, you're going to have this button right here. If you're having a problem with this, just let me know and we'll figure it out. Right? So if you click this, they give you a lot of functions here, and in fact, we talked about correlation, and correlation is already here too. So we can do that. And descriptive statistics is already here. This is mean, variance, and everything, right? So why don't we just try that? Why don't we just first use, we're gonna use regression here. So we're gonna use that. So press regression and press OK. And then it's asking for input range, input Y range. Okay, so for Y we're using drying time. So we're gonna use the value for here, right? These are the Y values, and for X we do the same, but we choose concentration. So press enter, and we have it here. So Y and X are um, are included in the system. And yeah, why don't we just create a new worksheet, and we're gonna name this paint result. Okay, and for now, um, um, okay, let's just not worry about these yet. So just press OK. And if you go to the regression, the next tab, paint result, as I named before, it looks like this. Okay, so let's discuss what these are. So first of all, it gives you a table here, and these are the regression statistics. Okay, and these are what we're concerned the most about. Okay, so this is the one to look for, regression statistics. Okay, and now let's look at some other things. Here, it says multiple R. It just means, I'm not sure if you remember this number. This looks familiar, right? This means correlation coefficient. Okay, so we already calculated this number, so this is 0.8, which is correct. And R square, okay, this is another very important measure, and we're not going to talk about how to get this because it's pretty complicated. But just for now, just think about this as the following. So 64% of the data is explained by the model. Okay, so 64% is okay, but it's not really that high. It's okay, but it's not that high. We want it to be somewhere in 80s or 90s. The closest it can get is 1, which is 100%, which means that we have found the most perfect model for the data, right? So the rest 36% is not explained. So it's saying that there is a variance. There are a lot of um, there might be other variables that are not explained by these data. So 60% of the data is explained by the model, and that's what we mean by R squared. Okay, and adjusted R squared, standard error, we're not going to talk about that. Observation just means number of observations, so that's n. And we're going to talk about these. Um, these means like degrees of freedom, regression, residual, right? Intercept and x variable. These are um, what we use to verify if B1 and B0 are significant. So what it's saying um, is it really okay to use these measures, use these numbers, right? Slope and intercept to estimate and make a prediction. And it's saying um, it's showing the coefficient, the standard error, and so forth. And we're going to talk about this later on. But just don't worry about this for now because we are not concerned with this just yet. So just look at multiple r, r squared, and these are the most important things that we need to be aware of. All right, so that's that. And going back to Paint. So, right. So that's how you do linear regression. That's pretty much in a nutshell how to use that um, the the Excel program because it's already built in, so it's really good. But another thing, when I think I briefly mentioned this before, but whenever we're building a model, right, we have to comment on the errors, right? It's virtually impossible to have a perfect model where you don't have any error, right? You some if it's small, it's a good thing, but there is always an error that you have to make sure that you cover in your report or when you're commenting, when you're making a model that you have to let the users know about, right? I'm not sure why this is not working. Okay, it's working. Okay. Alright, so we're going to talk about errors, or in this case, we call this residual. Okay, so say we have a plot and we came up with this line, and this is y hat equals b0 plus b1, and with hats x, and this is the line that we came up with. And there are observations here, there, and some along these lines. Alright, so we have these observations and we have a line over here, and this is a predicted line, and we call that a linear regression, which is represented by this equation right here, and we have all these observations, and we do have some kind of discrepancies here. If you look at it, there is no such thing as the perfect model, so we do have these differences between the prediction and the sample value, right? And these are called residuals. Okay? And it is represented by E. And we do this observed value minus predictive value. Okay, so this is also known as y, right? This is the value y minus y hat. That's the prediction. When we're doing a prediction, we always put a hat over it, so that's y minus y hat, right? And you have to be careful with the term. I think I used this in a misleading way too, but the difference between residual and error, okay? Residual is always looking for the difference between observed value and the predicted value, right? So these are observed values, and all these observations are what? These are samples. And when we talk about the error, right? Error is always the sample value, the difference between sample and the real value. The real value meaning the population value, right? Okay, so just to make that clear, um, what are some characteristics of these residuals? All right, so we see that residuals are some of them are positive, some of them are negative, right? And the sum of all residuals is always what? What do you think it is? It's always 0. Because that's how we came about this line, because we wanted to minimize the values, right? And we wanted to um, that's why we square the values, but when we are adding all these values, we always get 0. That's how we fit this line into the model, right? So this is 0, always 0. So sum is 0, and also the mean is 0 as well. So E bar is always 0. Okay? And another thing, so these are the characteristics of residuals. Okay, so first, they're all 0. And 2, if the model is significant, meaning that it represents the value correctly, then residual plot is random. Okay, it makes sense because residuals, it's supposed to be random. It has to be all over the place. If you um, draw the plot for residuals, and if you see a pattern there, then there is something else. That there is something that you're missing from your model. Okay, so residual plot. Let's just go up a little. Residual plot looks like this, right? Um, so this is 0, and all the residuals are randomly placed. Okay, so it has to be random. And this is when the model is significant. And if there is a pattern, something like if you draw the residual plot, and if there is a pattern, then you're using a wrong model. That means there is a pattern that you did not cover in your model. Okay, so that's how a residual plot works. Okay, so random pattern. So always when we are doing regression, we have to make sure to include that as well. So why don't we just do that? Let's go back to data analysis, and let's choose regression. And we're going to do the same. We have Y range and we have X range. And here we have residual as an option, right? Residuals, we're not going to look at the standardized residuals, but we are going to look at the residual plots. Okay, so press OK. Okay, there was a problem with it, but it did it. Alright, so this is the residual plot. Alright, so some of them are negative, some of them are positive, and there seems to be a pattern like that, but we can't really tell because there are only 5 observations. But if you have more than 5, if you have a lot of observations, it will be easier, much easier for you to tell if it's random or if there is a pattern. And whenever we're using this linear regression, we have to include this residual plot, and you have to comment on it. So you have to make sure that the residuals are all random, and if there is a pattern, then you have to talk about it and you have to move on to another model. So that's let's see if that's pretty much it about linear regression, and I think we're just gonna do some examples now because it's always practice, right? That's what we do. Alright, so let me just see if I'm missing anything, and we can just move right on. Alright, so let's just move right on. And this is the body versus weight that we did before. Oh no, this is not body versus weight. That's the paint. Oh, okay. So let me just copy over the data from previous class. I'm gonna do body length versus weight. So let me just copy this over back to here. Alright, so this is body length. Let me just label this body length. And for y, we have weight. Okay? And we're gonna do the same linear regression, right? So I mean, we can do the mathematical way. For your class activity, I'm gonna give one for you to work on it manually. But for this, we're just gonna use the data analysis tool package. Okay? So let's just go straight to data analysis. Okay? And we have regression again. So press that, and you have to give it a range. So this is the y range, and this is the x range here. So let's see. Okay, so these are all correct. And then we're going to do create a new worksheet. So let's just say body weight result, and we're going to include residuals and residual plots. Okay, so let's see. All right, so let's look at the summary output first. So these are the regression statistics. Let's make it a little bigger so you can see. Zoom in. Okay, so these are the regression statistics. So we did multiple R. So this is the correlation coefficient. So before using regression, you always have to check the R value if it's linearly correlated, and we see that with the 7.73, that's roughly there is a positive relationship going on, and R square unfortunately is pretty low. That means this is 55% of the data is explained by the model. So that's pretty low. But there's nothing else we can do about it because we didn't learn about any other models yet. So these two are important ones. And standard are we're not going to talk about this yet, but observation was 8. And moving on, we're not going to look at these values. But if you're looking at this, we're looking at the residual plot. Okay, so what do you think? Do you think there is a pattern? I would say, yeah, it looks random to me, but except for this value, right? This is an outlier, right? There shouldn't be an outlier when you're looking at the residual plot. Outlier is something that's way out of range. So all the other ones are located around here, but there is only one over here that's left out. So you have to make a comment on this, and you have to check which observation this is from, and you would have to make sure to comment on this when we are doing some kind of report. Okay, so that's how you would talk about it. So for commenting on the residual plot, everything else looks fine except for this observation. There seems to be an outlier. I mean, we're not 100% sure because it's only what? It's only 10 13-ish difference between all the rest, but still we have to mention that it might be an outlier, so it gives you some kind of full answer to the problem. All right, so now I'm going to give you a class activity. So let's all right, so I'll let you work on this. So this was part of your homework. This is a question 1 from yesterday's homework, and we want to use this data to look at the linear regression. Oh, Sorry, for this we forgot to do the linear regression. Sorry, we forgot to come up with the um what is it, the coefficient and the intercept. So we will do that now. But before we do that, it gives you the observation number, and we have the predictive value here, and we have the residuals. So we see that so we see from here that this value right here, which is far from here, all the rest we can figure it out from these table, right? So I think that seems to be either, it looks like this one, but we would have to investigate that, right? So let's just do the linear regression now. Okay, so to look at the values for intercept and the slope, here are the values given in this table. So we're not going to talk about standard error or t-statistics yet, but we can look at the coefficients here. So intercept, this just means b0. That's what we were talking about before, right? Y-intercept. And that's the value right here. So these are the values for intercept, and one x variable 1, that is b1. Right? So this is the slope. You can use these values to come up with the equation, or there's another way to do this. So if you go to the data set, the raw data, we can create a chart again. So go to insert and then scatter plot, right? And this is a scatter plot. Make it bigger. We see the values here, and we learned how to create a trend line, right? So you click it off, and on the right side you see a right arrow. If you click that, it gives you options, right? Linear, exponential, linear forecast. But we didn't learn about that yet. So if you can choose linear, and also you can go down to more options here. Click that, and there is an option here for Excel to display the equation on chart, right? So you can click that off. You can also display the R squared value on chart, so that you can do that too. So R squared is given, but let's just do the equation first. So if you click that, and I'm not sure if you can see, but there is an equation given here, and that corresponds to the chart from here. So we just highlight these. These are the values we need, okay? And multiple R is correlation coefficient, and R square is always the percentage data that is explained by the model, right? And I think that's about it for now. All right, so for question 1 from your homework, I want you to do the same, but I want you to do InMape versus cell phone. So let me just write it down here. InMate versus cell phone, and you're gonna find correlation. I think correlation coefficient we found already. So linear regression. Okay, so you're gonna find a linear regression, and you're gonna come up with the equation first of all, and next you're going to look at the residual plot, and comment. You have to comment. It's always important to comment on it. So residual plot, and comment if the residuals are random, or if there is any pattern you see, right? So linear regression and comment. All right. And before I move on, sorry, I keep forgetting some stuff that we go over. So looking at this here, we came up with the equation, right? If you come up with the equation, if you know the b hat 0, b1 hat, right? If you want to make a prediction, we can just plug in any value for x and you will get a prediction, correct? So using that logic, um, going back here, we can see that if, no, here, so the equation here is given. Let me just make it a little bigger so you can see. I'm not sure if I can do that though. Alright, I don't think I can do that. Alright, oh well. What if we are looking for a value on 130 because we don't have 130 here, right? So if you were looking for that, the value of 130, then, so we don't have 130 here, but we want to make a prediction for 130 for x. So we use this equation that we were given before, this one, right? So we're going to do equals 1.0548 x times x was what? 130. This is the number that we're looking for. X and minus 59.695. So I'm using this equation right here to make a prediction for 130. And this is the value that I was given, 77.43, right? So if you go back, if you kind of look through here, so 130 is this line, right? If you go up, this is the value that it's predicting, 77.43, right? So you're gonna make that prediction as well. So for that, you're gonna do inmate versus cell phone. You're gonna run a linear regression. So you're using the data 2, analysis 2 package, and then you're gonna draw the residual plot and comment, and you will also make a prediction. For, say, 1.6. Okay, no, let me just write it down this way. X equals 1.6. Okay, so you will do this for inmate versus cell phone, and also you will do this for inmate versus motorcycles. Okay, so that's your classwork for now. I want you to work on it, and let's come back and talk about it. Okay.